All right, May 3rd through the 7th, Lesson 13, Relationships between two numerical variables. All right, today what we're going to do is we are going to look at how to talk about scatter plots and the relationship that we can see modeled by the linear equation and some by nonlinear equations. All right. So it says not all relationships between two numerical variables are linear, which we learned about linear relationships last time. There are many situations where the pattern in the scatter plot would be best described by a curve. Two types of functions often used as modeling nonlinear relationships are quadratic and exponential functions. Sometimes the pattern in a scatter plot will look like the graph of a quadratic function. So this is a quadratic function with the points falling roughly in the shape of a U that opens up or down as in the graph below. All right, so our U-shaped is our quadratic function. In other situations, the pattern in the scatter plot might look like the graph of an exponential function that either are upward sloping or downward sloping. So, guys, kind of think of the exponential function as maybe half of the U, where it's either sloping up or it's sloping down. All right? So we're going to look at these 5 scatter plots that we have discussed in previous lessons. All right? I think they were in Lesson 12. So I want you to take a minute and look at those. And then let's look at which of the 5 scatter plots from Lesson 12 show a pattern that can be reasonably described by a quadratic curve. All right, remember a quadratic curve is our U shape. So let's look at this. This kind of seems like it might have somewhat of a linear relationship. Looking at this one is not a full curve. All right, it's not that full U shape. Here, this is one of those that looks like they just kind of plopped the paper down. All right, it's scattered everywhere. Look at scatter plot number 4. It has a U shape. It's rough, but it has a U shape. And look at scatter plot number 5. All right, once again, it's kind of scattered there. It's not in a U shape. So we're going to say for number 1, scatter plot 4. Which of the 5 scatter plots show a pattern that could reasonably be described by an exponential curve? Well, going back over these, the only one that looks like half of the shape of a U would be scatter plot 2. All right, so go ahead and fill those in for number 1 and number 2. All right, let's revisit the data on elevation in feet above sea level and the mean number of clear days per year. The scatter plot of this data is shown below. The plot also shows a straight line that can be used to model the relationship between elevation and mean number of clear days. In grade 8, you informally fit a straight line to model the relationship between two variables. The next lesson shows a more formal way to fit a straight line. The equation of this line is y is equal to 83 6/10 plus 8 thousandths x. All right, so let's use that information. So it says, assuming that the 14 cities used in this scatter plot are representatives of cities across the United States, should you see more clear days per year in Los Angeles, which is near sea level, or in Denver, which is known as the Mile High City? Justify your choice with the line showing the relationship between elevation and mean number of clear days. Well, if you will look at this, according to our graph, as the elevation increases, so does the mean number of clear days. So if Los Angeles is near sea level and Denver is the Mile High City, that means Denver has a higher elevation, so therefore Denver should have the number of clear days. All right? So we're going to say Denver because as elevation increases, so does the number of clear days. Okay. All right. One of the cities in the data set was Albany, New York, which has an elevation of 275 feet. If you did not know the mean number of clear days for Albany, what would you predict this number to be based on the line that describes the relationship between elevation and mean number of clear days? Well, I have the equation for my line, so I can let x equal 275 and then substitute the value into the model. All right, remember the model in this case would be our equation. All right, so when I do that, all right, so our equation was 83 6/10 plus 0.008 times 275. So we get approximately 85 8/10 days. Which we know would be about 86 days. All right. Another city in the data was Albuquerque, New Mexico. Albuquerque has an elevation of 5,311 feet. If you did not know the mean number of clear days for Albuquerque, what would you predict this number to be based on the line that describes the relationship between elevation and the mean number of clear days? So once again, here we're going to let x equal 5,311 and substitute it into our model. So then I'm going to do 83 6/10 plus 0.008 times 5,311, and I get approximately 126,088. So that is about 126 clear days. All right. All right, let's look at number 6. Was the prediction of the mean number of clear days based on the line closer to the actual value for Albany with 69 clear days and for Albuquerque with 167 clear days? All right, so the line predicts that Albany would have 69 clear days, all right, and Albuquerque would have 167 clear days. So was it close? Well, the prediction was closer for Albany than it was for Albuquerque. So the prediction was closer for Albany. All right, they predicted 86 clear days, or I'm sorry, they predicted 69 clear days and we got 86. Where Albuquerque, they predicted 167 and we got 126. All right. How could you tell this from looking at the scatter plot with the line shown above? The distance from the predicted point on the line to the point representing Albany shows a smaller distance than the point corresponding to Albuquerque. Alright, so I could go back and I could look at my point and I could find where Albany was 275. So Albany's somewhere around in here. And then Albuquerque was 5311. So Albuquerque was somewhere around in here. Alright, so I can see that my line from the point to the line is smaller here than it is here. Alright. Alright, example number 2. So let's talk about something really quickly. Is fertilizer good for plants? Well, you can say yes, because it does help them grow. It gives them nutrients. But can a plant be over-fertilized? Yes, it can. How can we find the amount of fertilizer that produces the most corn? Well, that is what example number 2 is looking at. Farmers sometimes use fertilizer to increase crop yield, but often wonder just how much fertilizer they should use. The data shown in the scatter plot below are the study of the effects of fertilizer on the yield of corn. Alright, so let's look at this. This is the amount of fertilizer versus the amount of corn it's going to produce. Notice what happens. But then what happens here? It kind of gets a little bumpy there. Alright, so let's see what our questions ask. The researchers who conducted this study decided to use a quadratic curve to describe the relationship between yields and the amount of fertilizer. Explain why they made this choice. Well, if you look in the beginning, the amount of fertilizer increases, so does the yield. But around 250 kilograms, then my yield begins to decrease. Alright? So that's why they chose the quadratic curve to explain this. So in the beginning, as the fertilizer increased, so did the yield. Alright, so we saw that. As they increased the amount of fertilizer, the amount of yield started to increase also. But around 250, kilograms, the yield starts to decrease. As the fertilizer increases. Alright, so what we can say is they're probably over-fertilizing the crops. Alright. The model that the researchers used to describe the relationship was y is equal to 4 7/10 plus 5/100 x minus 0.0001 x squared, where x represents the amount of fertilizer and y represents the corn yield. Use this quadratic model to complete the following table. Then sketch the graph of the quadratic equation on the scatter plot. Alright, so we're going to go ahead and figure this out. Alright, so as we enter this in into the calculator, I'm going to let x equal 0. Well, if I let x equal 0, then all I'm going to get is 4 7/10. All I'm doing is plugging 0 in for x here. Alright? If I plug 100 in, let's see what I get. I get 8 7/10. If I plug 200 in for x, I get 10 and 7/10. All right, let's plug 300 in for x. I get 10 and 7/10. Notice what's happening there. Plug 400 in, and I get 8 and 7/10. All right. So now it says, go ahead back to the graph, and let's plot that curve. Well, with x being 0, it was about 4 and 7/10. So my curve's going to start here. When x was 100, it was about 8 and 7/10. So we'll go about right here. All right. Then we've got 200 was 10 and 7/10. All right, so my curve is going to go about like this. All right, it's going to go about like that. Based on the quadratic model, how much fertilizer per 10,000 square meters would you recommend that a farmer use on his cornfield in order to maximize crop yield? Justify your choice. Well, where are we going to get the most crop? It's going to be somewhere between 200 to 250. All right? I would not go any more. All right, so I would go 200 to 250. Because if he starts going over 250, he's going to start over-fertilizing, and his crops are going to start dying or not producing as much. All right, an exponential model. What is meant by regulating lobster trapping? All right, that is preventing commercial fishermen from harvesting too many lobsters. They don't want commercial people coming in, getting the lobster, so they're regulating that trapping. Why would biologists care about the age of a lobster? This information can be used to decide whether lobster can be harvested or thrown back into the ocean. If it's too young, they're going to throw it back. They want to make sure that it's right at the right age. Now, why are we talking about this? Well, let's look at the next example. How do you tell how old a lobster is? This question is important to biologists and to those who regulate lobster trapping. To answer this question, researchers recorded data on the shell length of 27 lobsters that were raised in the laboratory and whose ages were known. All right, so go ahead and look at that data. The researchers who conducted the study decided to use an exponential curve to describe the relationship between age and exterior shell length. Explain why they made this choice. Well, we see as the shell gets longer, the age of the lobster increases. All right? So as the length of the shell increases, so does the age. There's no up-down to this part. It continually goes up. All right? All right. Based on, the model that the researchers used to describe the relationship is y is equal to 10 to the negative 403 thousandths plus 63 10,000ths x, where x represents the exterior shell and y represents the age of the lobster. The exponential curve is shown on the scatter plot below. Does this model provide a good description of the relationship between age and exterior shell length? Explain why or why not. So does the line that they have drawn, the exponential curve that they have drawn, does it do a good job of describing that relationship? Well, it it is close to the majority of the points, so the model does a good job of describing the relationship. Alright? The data points lie very close to that model. Based on this exponential model, what age is a lobster with an exterior shell length of 100 meters? Alright, well, looking at the graph, 100 meters would be around 1/7500 years old. Alright, so we can say about 1/7500. Alright, from the model, I would plug in 100 for x, and when I do that, meaning I'm plugging 100 into this x right here, I'm going to get approximately 1/6900 years old. Alright, so pretty close. Suppose the trapping regulations require that any lobster with an exterior shell less than 75 millimeters or more than 150 millimeters must be released. Based on the exponential model, what are the ages of lobsters with exterior shell lengths less than 75 millimeters? Alright, so let's look at what are the ages less than 75 millimeters. So that would be anything less than a year old. So for 75 millimeters, anything less than a year old. Alright, what are the ages with the exterior shell length of greater than 150 millimeters? Let's go and look at 150 millimeters would be, what, 3.5 years old? So anything over 3.5 years old. So if the lobster is less than a year old, they would have to let it go. If a lobster is older than 3.5 years old, they would have to let it go. Okay? And that's just based on the model. Alright guys, that's the end of the lesson. If you have questions, reach out to me. Hopefully you didn't find it too difficult. Have a great rest of your day.